Hello everyone, I'm Zhuming Jiang from Tsinghua University. It is my pleasure to be here to present our work, Context-sensitive and Directional Concurrency Fuzzing for Data Race Detection. I was lucky to work with Dr. Jiajun Bai, Professor Kangjie Lu, and Professor Shiming Hu. As we know, data race is a common class of concurrency problem. It happens when two memory operations concurrently access a same memory location, and at least one of them is a write operation. This is a data race from JFS file system. The variable in blue blocks point to the same memory location, and this operation can be concurrently executed. So there's a data race. When the data race occurs and the read operation from thread 1 happens before the write operation from thread 2, the raised variable becomes null and finally lead to a null pointer dereference. Data race is common in both user level and kernel level program. If important data is raised, it could cause critical security issue like privilege escalation. However, dynamically detecting data race remains a challenging research problem because of the non-determinism of thread scheduling of testing program. Encouraged by the promising result of fuzzing, developers have used existing fuzzing tools with data race checker to detect data races. For example, we could use AFL and TSUN to detect data race in user level program and could use Syscaler and KCSUN to test kernel level program. However, these two are limited in testing concurrent program because they mainly use sequential coverage feedbacks like branch coverage, which do not involve any concurrency features. And they also lack a technique to explore thread interleavings. To address these problems, several concurrency fuzzing approaches are proposed. They use new coverage metric and try to explore thread interleavings. However, they are still limited because their coverage metric are context insensitive and they perform random thread interleaving exploration. Here is the data race we mentioned before. In fact, these two functions could be concurrently executed in two different contexts, namely co-pair 1 and co-pair 2. However, the data race only occurs in co-pair 1 and never happens in co-pair 2. The existing fuzzing approach identified these two thread interleaving as same, so they easily miss-budget thread interleavings. Moreover, the thread interleavings in co-pair 1 is infrequently executed. As we know, the data race has existed over 15 years, so it's quite difficult for existing fuzzer to detect this data race by just randomly exploring thread interleavings. To tackle this problem, we propose a new concurrency fuzzing approach. This approach mainly consists of two techniques, a context-sensitive concurrency coverage metric, concurrent co-pair, and a directional thread interleaving exploration. The exploration uses adjacency-directed mutation and a new breakpoint control method. Our context-sensitive coverage maintains the information of each function call, which include the location where the function is used and the location where the code function is defined. Here, and we maintain calling context, which consists of the listed function call in the runtime call stack. Our new coverage metric, concurrent co-pair, consists of two calling contexts of two concurrently executed threads. By using this coverage metric, our fuzzer could identify the thread interleavings in different contexts. Similar to AFL, we store the concurrent co-pair as a hash value and keep its occurred time. Based on our concurrent co-pair, we first propose directional thread interleaving exploration. The right-hand side is the overview of the fuzzing loop. Before fuzzing, we first inject code breakpoint in the testing program, and then we run the program and collect its runtime information. Based on this information, we perform adjacency-directed mutation to generate possible new concurrent co-pair, and then perform breakpoint control to deterministically cover the possible concurrent co-pair. Finally, we go back to step 2 and continue our fuzzing loop until we reach the time limit. Here we can know that adjacency-directed mutation and breakpoint control is our key technique. Let me introduce adjacency-directed mutation. This mutation aims to infer possible thread-interleaving for subsequent exploration. It is based on a basic inference. Suppose that there are two functions, function A and function B. They are observed to be concurrently executed with calling context A and calling context B respectively. And function B and function C are observed to be adjacently executed with calling context C and calling context B. It is reasonable that we infer function A and C could possibly be concurrently executed with some thread scheduling. Similarly, if function D and function A are executed adjacently, we could infer that with some thread scheduling, function B and function D could be concurrently executed in corresponding calling context. Here is an example showing that how our adjacency-directed mutation works. From the observed program execution, we could generate a covered concurrent co-pair which consists of calling context A and B. Then we identify the adjacency function of function A and B and identify their calling context. So we get function A minus 1, A plus 1, B minus 1, and B plus 1, and their calling context. We use this calling context to infer new possible concurrent co-pair, which consists of calling context of A and B and the calling context of their adjacent functions. Finally, we drop some concurrent co-pair which is already being covered. Based on these inferred thread-interleavings, we could try to cover this. However, thread-interleaving is often non-deterministic, so covering specific thread-interleaving is difficult. To address this problem, we propose deterministic breakpoint control. The following is the workflow. Suppose that we want to cover the concurrent co-pair which consists of calling context P and Q. First, if we observe that function P is executed with calling context P in thread 1, we enable the breakpoint in function P, and which will block its thread. And then we continue to run the program. Given a time limit, if function Q is also executed with calling context Q, we just disable the breakpoint and record that this co-pair is covered. Otherwise, if we reach the time limit but could not execute function Q with calling context Q, we also disable the breakpoint. By this way, we can actually cover the inferred concurrent co-pair if it could be covered. However, there is another problem. How many concurrent co-pairs should be handled in each time? If two field co-pairs are handled in each time, it will cost too much time to try to cover all concurrent co-pairs. If too many co-pairs are handled in each execution, it will introduce too much overhead in each execution. So to solve this problem, we propose adaptive breakpoint control, which refers to TCP congestion control. The workflow is shown as follows. We get inferred concurrent co-pair from adjacency-directed mutation and initialize select num as 1. And then we randomly select concurrent co-pairs. The number is select num. We perform deterministic breakpoint control according to the selected co-pair. After that, we check whether some of the selected co-pair are covered. If so, we delete the current co-pair from the pair set. Otherwise, we double the select num. Finally, we check whether select num is less than pair num and decide whether the workflow should be stopped. Based on the technique we propose, we implement a concurrency fuzzing framework, CONCER. It performs context-sensitive and directional thread-interleaving exploration. To detect data race, we implement a customized race checker for CONCER. We evaluate CONCER on a user-level application and 4 kernel-level file system. The time budget is 24 hours. We repeat each fuzzing process 5 times. Here is the race detection result. CONCER in total find 95 real races. Among them, 75 are harmful and 34 have been confirmed. Among the races found by CONCER, 77 occurs on accesses to data structure fields stored in heap memory, and only 18 occurs on the accesses to global variable. And 53 data races involve function pointer calls, which is hard for static analysis to handle. In addition, we noticed that 5 data races occurred in program initialization or finalization process. These races could cause a critical issue because these 2 processes usually handle important data. To evaluate the effectiveness of each technique used in CONCER, we performed sensitivity analysis. We set up substitutive tools, namely normal running, which just repeatedly run the tested program, random delay, which inject random delay in each executed function, and insensitive, which use context-insensitive coverage feedback. The evaluation result show that CONCER outperform these tools and find more bugs in all tested programs. We also compare CONCER to state-of-the-art fuzzer with data race checker, such as AFL++ and TSUN, Syscaller and KCSUN, and InstFuzzer and our customized checker. InstFuzzer is a substitute tool which use instruction pair and perform random thread interleaving exploration, which is similar to another state-of-the-art fuzzer, K-race. In terms of thread interleaving exploration, CONCER covers more concurrent co-pair than other fuzzers because it uses context-sensitive and directional thread interleaving exploration. In terms of race detection, CONCER finds more data races than other fuzzers because it covers more thread interleavings. CONCER could also find races hiding in infrequently executed thread interleavings. Finally, let's conclude this work. We find that existing concurrency fuzzers could not explore thread interleaving effectively due to their context-insensitive coverage feedback and random thread interleaving exploration. To solve this problem, we propose CONCER, which uses context-sensitive concurrency coverage, namely concurrent co-pair, and perform directional thread interleaving exploration. In evaluation, CONCER finds 95 data races in 8 applications and 4 file systems. In comparison, CONCER outperforms other state-of-the-art fuzzers. That's all of my presentation. Thank you for your listening.